Okay, I just messed something up, so I'm starting over. We've got our VC and our VL, and remember our VR was R times I max times the sine of omega t plus phi 1. So let's think about how VR would go into this diagram. Where is the sine function going to go compared to the cosine and the negative of the cosine function? Okay, well, let's just draw an x and a y axis here. I'm going to draw a graph representing a sine function. And the phase for this sine, the phase angle for this sine function is 0, since the sine function starts right here at t equals 0, let's say. Now, it'd still be a perfectly good sine function if I wanted to move the origin to some other, or if I wanted to move the vertical axis to some other point. We would accommodate that just by changing this phase angle. Okay, well, let's look at the capacitor voltage. Okay, capacitor voltage is 1 over omega c, whatever that happens to be for this capacitor and this frequency, times the cosine of omega t plus phi 1. Now, in the first place, we don't know how big or small this is compared to, well, we don't know how big or small this amplitude is compared to this amplitude. Okay. I see something else I did over here that's just really pretty ignorant. I'm going to have to go back and talk about that. Okay. Not having a great night tonight. I don't know why. Okay, so really, this shouldn't be 1 over omega c. This should be I max over omega c, and this should be negative I max omega L, and it should have been before. That doesn't really change the picture, except there should be an I max here where you can't read it, and I max here in this picture. It doesn't change the essence of the picture, it just changes the scale. Okay. Now, capacitor voltage is this, and it's just a multiple of the cosine. We don't know how big this amplitude is here compared to this amplitude, so we could use anything, but let's just say it's got an amplitude fairly comparable. So what would the cosine graph look like? Well, a cosine graph, as you know, starts here if the sine graph starts here. And the cosine graph does this, reaches its minimum here, comes back up to 0 here. Okay, it does this sort of thing. So this will be your V sub R, and this is your V sub C, and it's pi over 2 or 90 degrees behind the V sub R, isn't it? Okay. Now what about the V sub C, the negative cosine? Okay, it's a negative multiple of the cosine, so I'm going to give it a little lesser amplitude, but the negative multiple of the cosine is going to start down here and come up to 0. And it'll come to a maximum, and it'll come back to 0 here, come down to a minimum, come back to 0 here. So this would be like your V sub L. That would be this. And that is 90 degrees ahead of V sub R. Because, of course, it peaks here when V sub R is peaking here, and the V sub C is peaking here. So you have your V sub R with the inductor voltage V sub L 90 degrees ahead of it, and the capacitor voltage V sub C 90 degrees behind it. Well, how does that work on the picture? Well, here's V sub C. 90 degrees ahead of that, you have your V sub R. 90 degrees ahead of that, you have your V sub L. Of course, V sub C and V sub L are in opposite directions, just as they always have to be. But right here's a picture of our phasor, and if we follow this diagram as it rotates, and our actual V sub C here, our actual V sub L here, and our actual V sub R, which happens to be pretty close to the actual V sub L at this point. All these vectors projected onto the x-axis, which I screwed up and drew too low. The x-axis should actually be up here. And I did screw up and do that, but it's just as well because I want to draw these vectors and don't really want the axis in the way. But the axis should be right on top of all these horizontal vectors. Okay, so at this moment, there's our V sub C, there's our V sub L, there's our V sub R. Now, if we put our V sub L together with our V sub R, they're pretty close to V sub C. So it could be right at this instant, all these things cancel out. But if they proceed a little further on, V sub C is going to decrease a little bit. V sub R is going to increase pretty fast. V sub L will decrease somewhat. What happens? Well, it's fairly easy to see what actually happens to the current because we can add these three vectors in two-dimensional space. Okay, this vector and this vector, well, if we take this vector, put it head to tail with this one, we get this little vector that I've just kind of drawn lightly here. That's our total of our V sub L and our V sub C. We put that together with V sub R, we draw our rectangle here and draw the diagonal, just use a parallelogram method to do this. We get our V total. It looks like this. And no matter where these things rotate, V total is going to keep the same magnitude. It's just going to rotate along with the rest of the picture. So we're going to see our V total rotating around here. So if we move this thing almost 90 degrees, our V total is going to be close to its negative maximum. Well, that's a picture. This is a picture how our inductor, capacitor, and resistor voltages go together to give us our total voltage. And we put this into the unit circle picture, get it rotating with angular frequency omega, and we have a model of our circuit's response. Okay, so that's kind of a big deal. And it's kind of a simple picture once you get used to it that embodies what happens with all the differential equations. Okay, if you don't have a V sub R, then your V total is going to be along this line, depending on whether VC or VL is bigger. So you can play around with bigger and smaller V sub Rs, bigger and smaller V sub Ls, bigger and smaller V sub Cs, and see what happens.